Previously on Math Hands-On with Python. Hello everybody, welcome back to Math Hands-On class with Python, and today we are going to have a lecture session on the operation research. The topic is called the transportation problem. So we have the main objectives in this lecture session. So the objectives here, you should be able to describe transportation problems, structure linear programming for transportation problems, use the NorthWest corner method in developing an initial solution to a transportation problem, and also use the stepping stone method to evaluate an initial solution to a transportation problem. And lastly, you should be in a position to apply the knowledge and skills in solving facility location and other application problems. Let's continue. So, in general, a transportation problem is concerned with the determination of this optimal strategy for the distributing commodity from a group of supply centers such as factories called sources to a various receiving centers such as warehouses called destinations. So in such a way to minimize the total distribution cost. So here we have a network model showing a number of factories producing similar products, exporting to different destinations, which we call warehouses. Okay. So each source is able to supply a fixed number of units of products, basically, usually called the capacity or availability, and each destination has a fixed demand, often called the requirements. Now, we have an example here we are going to use to set up a transportation problem. Consider we have a concrete company which transports concrete from 3 plants, different areas. We have plant 1, 2, and 3, to 3 construction sites labeled as A, B, and C. But the company have allocated the supply capacity, okay, for each plant, okay, in tons per week. We have 3 plants, and this is its supply capacity of the concrete. And also we have information about the requirements of the construction sites. So we have the requirements in ton per week. We have the demand or requirements, as you can see here. And lastly, the information we have here below is the cost of shipping or transporting or supplying this concrete from the plants to the construction sites. So you can see here inside the last table represent the cost of the transportation or shipping or supplying this concrete from plants to destination, which are construction sites. So from this information, we can summarize this information in a single table, and that table is of more basic importance because the summary of this information, all of these 3 informations in one table, is what basically leads us to a solution to a transportation problem. So you can see, we can summarize this whole information. We have this cost here in, okay? So the information inside here, this represents the cost, okay? This information represents the cost. And we have the total demand or requirements at the bottom. And at the last column here, we have the total supply capacity for each plant. Okay. So now we have summarized the information from the 3 tables into a single table, which is now convenient for computation of a transportation problem. So we have also a different way where you can represent the transportation problem. Basically, this is not it looks like a summary but this one is just a representation of the transportation schedule using the network diagram. You can see we have these nodes here representing the left-hand side nodes represent the source, and the right-hand side nodes represent the destination. And these lines showing with arrows, or this arrow, showing the movement of items or goods from the sources to destinations. And here we can put the cost, and sometimes we associate with the amount of goods transported from a source to a certain destination. After formulating a table or a summary table for solving or for the purpose of solving transportation problem, now we need to formulate a mathematical model that represents the information from the table. Suppose that let's say we have M sources, okay, and N destinations, and that this SI representing the units of commodities, like you can see here, okay, are available at a certain ith origin, and the demand for DJs, okay, these demands, DJs units is to be met at the J's destination, okay. So we have this SI units of commodity somewhere, okay, is S1, S2, or up to Sn, but it needs to be supplied from that point to a certain destination to meet the demand, the J's, at the J's destination. So also, if we have the associated cost of moving the items from the source to the destination as Cij, as you can see here inside, okay, now a mathematical model can be formulated as follows. So the mathematical model of a transportation problem is the minimization problem as a sum of the products between the cost and the associated goods at that destination. So this sum of these products comes from, consider this example, if we have 3 sources and 3 destinations, now the minimization cost function is the sum of this C11 times X11 plus C12 times X12 up to C33 times X33, okay, subject to supply constraints or capacity constraints, okay, which are the summation of these elements here, okay, X11 plus X12 plus X13, and this normally should be equal to this amount here, okay. And also we have the other constraint, which is the sum of the demand constraints, and this sum of the demand goes in the vertical direction addition, that is X11 plus X12 plus plus X21 plus X31 should be equal to D1. You add there, you have your constraints. So this is how you can formulate the mathematical model of a transportation problem. So we have a basic example that we illustrated, and we are going to show how we can develop a mathematical model from this table, okay. Now, after having this general table, then mathematical model, so this is the particular mathematical model for our problems, okay. And we have this table, which is represent the table of an example that we are using, and here inside these are the costs, okay. We have the demands for each construction sites and the supply capacity from each plants, okay. Now the minimization function is the sum of the products between the cost and its associated quantities supplied to that destination. So we basically add all sales cost multiplied to its associated amount of. So basically this is Xij are unknown still. So until we have a specific solution for this distribution. So this function basically is the minimization function subject to the constraint. This constraint here represent the supply constraint, and these ones represent the demand constraint. Make sure you have the non-negativity constraints at the end. Now after observing how we can develop a mathematical model for transportation problems, let's see how we can solve these the transportation problems. Okay, basically we have formulated the table, but before starting solving a transportation problem, make sure you check whether the problem is balanced or is not balanced. Okay, we are going to see that. And if the problem is unbalanced, you add the dummy row or dummy column. That means you add a dummy source or dummy destination, depending on which side is unbalanced. So, and whatever you will add, whether a dummy row or a dummy destination, that means a dummy source or dummy destination, it's that row or column, its associated cost should be equal to 0. The next step is to obtain initial feasible solution, and basically we have three solutions, okay, for obtaining this, for obtaining the initial feasible solution of the transportation problem. So we are going to use this northwest corner method, and these two, we are not going to discuss this, but we are going to use this northwest corner method to apply for solving the initial feasible solution. Now, look for this example how we can compute initial feasible solution using the northwest corner method from this table. So basically, as the method itself, it says we use the northwest corner. So we are going to start locating items or goods from a cell which is to the northwest corner, okay? Northwest corner from this cell of or matrix of cost, the north side is to this side and west is this side, and the corner is here. The northwest corner is the first row cell column, okay, here. So when we want to supply item at this construction sites, basically we have to look for the supply capacity and the demand. So we have the demand 200 and the supply capacity is 300. What we do, because this supply, this plant 1, it have the 300 supply capacity, which basically can fulfill these demands at these construction sites. So we pick 200 concrete here and we supply here. Okay. That means now plant 1 will remain with an excess of 100 concretes. Okay. Now that means this construction site, its demand will be satisfied, and no more sites will supply to these construction sites. Okay. Next, we remain with this matrix here, and again we look for the north but west corner. So the north but west corner is at this cell, and the demands is 200. The supply capacity is 100. So that means from plant 1, only 100 concrete can be supplied here, okay? And these construction sites will still need more 100 items, okay? 100 items more required for these construction sites, and here now is supply capacity have been satisfied. So since this plant 1 have used all its quantity, okay, to supply to construction site A and B, that means it cannot supply now to construction site C. Okay. Now you can see what remained is this cell here, and then you go to the north but west corner, which is this cell, okay, and the supply capacity of plant 2 to this is 300, while the demand is 100. That means this one can supply that 100, okay, and that means this construction site is satisfied, and here it remains the excess of 200 items. Okay, that means here also we cannot supply from construction site, from plant 3, because we have satisfied the actual demand of this construction site B, which is 200. Now we left with the northwest corner. Northwest corner, just 2 cells. We have north, but all of these are in a vertical position, so we just go to north. We don't have corner, and then we see the demand. The actual demand is 300. The supply from plant 2 is 200, so that means plant 2 will supply those 200. Okay, and that means its capacity is satisfied, and here the demand reduced to 100 because we have the 200 from the plant 2. So and plant 3 have the capacity of supplying 100. That means it will satisfy the remaining demand for the construction site C, and we are done. So this is the solution now, initial feasible solution of our transportation problem using the northwest corner. So this is the summary of what we did in this part here. So you can see this is the distribution. We have 200, 100, 100, 200, 100 as here. After having this distribution matrix, now we say this is the initial feasible solution. Basically, we can supply 200 items from plant 1 to construction site A. Okay. Also, from plant 1, also we can supply 100 items to construction site B. And from plant 2, we can supply 100 items at construction site B and 200 items at construction C. And from plant 3, we can supply 100 items at the construction site C. So this distribution of items from these plants will give us a minimum cost or a minimum initial cost of the products between the sum of the products between cost and the associated amount of quantities or commodities supplied at that cell. So it's a 4 times 200 plus 3 times 100, 5 times 100, 9 times 200, 5 times 100. You add all of that, and we have the initial minimum cost of 4,000. So this is the approach on how you can get the initial feasible solution of your transportation problems. Okay? Now, we have seen the first example, and now let's go to example 2. If the transportation problem is not balanced, how do we work on that? So in this particular table, we have told to use the northwest corner method to obtain an initial feasible solution. So the first thing is to determine whether the transportation problem is balanced or not. So if you check here, if you can add here, we have 800, while here we have 700, 900, and this is 1,000. So the demand is 1,000, while the supply capacity is 800. So you see that the demand is in excess, okay, exceed the supply by 200. That means our transportation problem is not balanced. We have 1,000 by 800, okay. So first thing, we need now to balance this transportation problem. So what are we going to balance? Because the demand is in excess, now we are going to add a dummy supply, because to this site we have a deficit of 200 supply items. Okay, so we add a dummy row, which is represent a dummy supply point with its associated cost of 0 transportation cost. Okay, because basically we don't have that source point. So we add for the purpose of balancing these transportation problems and make it easy to solve the problem. Okay, so if you balance this transportation problem, you add a dummy source with 0 transportation cost, and this amount here is the amount exceeded or is the excess amount from the demand, okay, which is the difference between the total demand and the total supply. So becomes the supply capacity for the dummy source. Okay, now after balancing this transportation problem. Now let's find the initial feasible solution using the northwest corner. So as usual, we go, this is the cell representing the cost, okay? Now we start with the northwest corner at this point, and we have the demand of 100, the supply capacity is 200, so we are going to have 100 here, because the supply capacity of the source 1 is more than the demand. That means we satisfy this, but here we have an excess of 100 items remained. Okay, so that means we have satisfied the destination 1, and we don't need more supply because the demand is 100 and we are done with that. So we go to the remaining cell. Okay, we go to the northwest corner. The demand is 200. Okay, and the supply capacity is 100 from source 1. So this one will supply this 100 items. Okay, so this will meet the maximum supply capacity, but here it will need more or excess 100 items. Okay, that means source 1 will have no ability to supply to other destinations. Now, we remain now with this 3 by 3 matrix with northwest corner at this cell with 12 as cost of shipping or transporting item from source 2 to destination 2. So we have the demand of 100 and its supply capacity of 300. That means this one can supply that 100. Okay, and this demand is met, but here we remain with excess or extra supply of 200. Okay, that means we have satisfied this destination and we don't need more supply at this one. Still we remained with this cell here. Okay, so the northwest corner is at this point. The demand is 450, while the supply is 200. So we supply those 200, and the supply capacity is met. And here we remain with the demand of 250. Okay, and that means this one have reached its supply capacity, and we remained with this one. Okay, so at this corner, this is the northwest one, we have the supply capacity of 300, the demand of 250. So this one can supply that 250. Okay, that means we meet this demand, but here we remain with an extra of 50. Okay, so we satisfied this one, we shared. We remain with these two cells. The north one is this one, so we are going to have 50 here, which is the remained one, because the demand is the 250. So we are done with this supply capacity, and we remain with 200 demand required, and the last dummy supply source have a quantity of 200. That means it can supply now here and balance the transportation problem. So we reach the supply capacity and we meet the demand required. So now you can see we have managed to allocate the resources from these sources to different destinations, and this allocation represents the initial basic feasible solution, and you take the multiplication of this allocation and its associated cost to get the minimum initial cost before you proceed to the next step. So thank you for watching. This is part 1 of the lecture, which I intended for you to learn on how basically you can build up a transportation problem from word problems, summarize into a table, you go to the mathematical model, and you solve the initial basic feasible solution. See you in the next lecture, where we can see how we can optimize this initial basic feasible solution using the stepping stone method to obtain the optimal solution. Thank you and goodbye.